Welcome back, everyone. In our last lecture, we introduced you to Anova and the F distribution. Now it's time to start using Anova to run some actual statistical tests. So the first test that we're going to talk about here is what is known as the one-way Anova, or more technically known as the single factor between subjects Anova. So that's going to be the goal of this particular lecture. Just like we've done with other tests, we're going to start with when do we use it. We're going to talk about some of the assumptions because it is a parametric test. And then I'm going to walk you through two hypothesis testing examples. One where we have equal variances assumed, one where we do not have equal variances assumed. The reading, once again, for this one is the same as it was for the last lecture. It's chapter 7 of edition 4 of your textbook. So let's go ahead and get started with our one-way Anova. Next slide. So when do I use a one-way Anova? Well, as you may recall, when we talked about Anova and the F distribution, it's when we're comparing three or more groups. So when we look under when to use, we see that come back to us. We use it when we're comparing sample means between three or more different groups to see whether or not the populations they represent are significantly different from one another. So this is where the F test and the one-way Anova is really just the next step past an independent samples t-test. You're going to see a lot of similarities between this test and the independent samples t-test. The key thing here is now we're using a new distribution, the F distribution, and we're not comparing just two groups, we're comparing three or more groups. So that's going to be kind of the key thing, and we'll see how that works out for us. All right, let's take a look at the variable requirements. For a one-way Anova, the independent variable, we are limited to only having one independent variable. That independent variable must be categorical with three or more levels or categories. So it could be something like we talked about in the last lecture where we looked at like current offense in one of the examples, and we had property, drug, and violent offenders, where once again, just bring back vocabulary, the factor in this case would be current offense, and then the levels of that factor would be property, drug, violent. So that's kind of the way that we want to make sure we're incorporating some of the vocabulary that we introduced in our last lecture. So one independent variable must be categorical with three or more levels. Then we look at the dependent variable. What are the requirements of the dependent variable for a one-way Anova? We are limited to one dependent variable, and just as we've seen with other tests, that dependent variable must be continuous. So it must be at that interval or ratio level of measurement. So there's an example down here, and this is one we will see towards the end of this lecture, that actually came from some real data that I worked with on a project several years ago, where we were asking the question, is there a significant difference in substance abuse problems across different racial or ethnic groups? So we can see how this fits the requirements of the one-way Anova. When we look at the independent variable, the factor, right? The factor is racial or ethnic group. Let's check to make sure it's categorical with three or more levels. Well, sure enough, our racial ethnic group factor is broken down into Hispanic, white, black, and other. So we have 4 levels to the factor racial ethnic group. So that fits the requirements for the independent variable or the factor. Then we look at the dependent variable. The dependent variable, let's make sure that it's continuous. Well, it is, the dependent variable for that example is substance abuse problem severity, and as you can see in parentheses, it is measured on a 100-point scale with higher values indicating higher severity. So it is, in fact, at that interval or ratio level of measurement. All right, let's go ahead and dive in a little bit deeper to the hypothesis testing steps of a one-way Anova. All right, so before we can begin the hypothesis testing, we need to make sure we are meeting the assumptions. So you may find this slide to be somewhat similar to, or actually basically the exact same as what we saw for the independent samples t-test. And in fact, the one-way Anova and the independent samples t-test have the same main assumptions. First, the dependent variable must be normally distributed within the populations of each group. But we don't have to worry about that too much as long as we have a decent sample size, because things like the sampling distribution of the mean and the central limit theorem will take care of that for us. 2, The observations have to be independent of one another. So whether we're comparing outcomes across different racial ethnic groups, or whether we're comparing some sort of outcome across different types of offenders, the key thing is we want to make sure that there's no dependence or correlation between any of the groups. Exactly the same as what we saw with the independent samples t-test. And then finally, our good old friend, homogeneity of variances, is back. So we saw it with the independent samples t-test, and it comes back once again for the one-way ANOVA. So the assumption is that the amount of variability in the dependent variable is roughly the same between all groups. And our good friend, the Levine's test, is right back alongside it. So we got used to seeing the Levine's test before. We're going to see it again. And the way that we interpret it is going to be just like we did with the independent t-test, where we're going to have a fork in the road and we're going to have to make the decision, can I assume equal variances or do I not assume equal variances? So let's keep going. Next slide. Hypothesis testing. Once again, we see our nice 6 steps of hypothesis testing, where we start with a statement of the research question, followed by translating that research question into 2 competing statistical hypotheses, the null and the research or alternative hypothesis. We set alpha. We then we'll talk briefly about critical value. We then need to figure out our observed value of the test statistic, and then we make our decision. So let's launch into an example of the one-way ANOVA. So in this one of the things you're going to see, just to make it somewhat so that I wasn't making things too small on the slides, I'm going to show you 2 slides that incorporate the Spss output. So in this first one, this is what you would typically see at the top of your Spss output for our one-way ANOVA. So at the top here, I've got the fancy term single factor between subjects ANOVA. That's the technical term. People more often than not just call it a one-way ANOVA. But if we had to break it down, it's nothing to be intimidated by. Single factor simply means we have one independent variable. Between subjects means we're looking for differences across or between the different levels of the independent variable, and it's an ANOVA. ANOVA just means we're doing an F test or an F distribution test. So in this particular example, let's make sure it fits the requirements of a one-way ANOVA. Our independent variable is the location of the police department. And you'll see that I've got it categorical, and it's broken down to having 3 levels. So our factor, location of police department, has 3 levels: rural, urban, and suburban. Then our dependent variable, we want to make sure that that fits the requirement of being a continuous interval or ratio level variable. And sure enough, starting salary is how we're measuring it, and we're measuring it in $1,000 per year. So let's look at the descriptives here. So the descriptives box, similar to what we've seen on other outputs, sort of gives us a breakdown of what our sample looks like. And so whenever you run a one-way ANOVA, Spss will, down at the bottom of the descriptives box, will have below the box the dependent variable listed. So you'll see there it says annual salary and then in parentheses in $1,000, just to make it simple. Then within the box, along that first column on the left-hand side, you will see listed the different levels of our factor, or the different levels of our independent variable. So we have rural, suburban, and urban. And the spirit of this one was, hey, if you're going into law enforcement, as much as you want to save the world and help communities, you also need to make some money. So maybe you want to know, is there a significant difference in how much money somebody's going to make if I get hired in a rural environment versus an urban versus a suburban? So in this case, we see that we have the 3 levels of our independent variable, rural, suburban, and urban, listed along the left-hand side. Then we have a pretty straightforward breakdown of the sample sizes for each group. And this happens to be what we'd call a perfectly balanced design. So balance, you may recall from a few lectures back. And remember, balance is, do we have equal sizes across the different groups in our study? In this particular one, we happen to have exactly 6 people in the sample coming out of a rural environment, 6 from a suburban, 6 from an urban, for a total of 18. Then we have the next column, which is the mean. The mean represents the average annual salary in thousands of dollars across those three different levels of that factor location. So we notice, looking at it, it appears that individuals getting hired in urban environments are making more money than individuals in rural or suburban, with urban being the highest at 47.5, rural being second at 43.17, followed by suburban at 36.666. Okay, so this is just our sample data. Our overall question is still going to be, just like it's been with other hypothesis tests, are those differences enough to say that we have a significant difference in starting salary across the different locations? And then the next box down that you'll see on the SPSS output is one of our good friends. It is our Levine's test, where it says test of homogeneity of variances. And then we've got our annual salary listed there. And here you may recall from the independent samples t-test that in the box for the Levine's test, they just listed as an F. Well, so that people don't get confused, because the Anova is an F and there's a lot of F's on the output for an Anova, they just write it down as the Levine statistic. And so you've got the Levine statistic, the degrees of freedom, and then it has a p-value, or that sig. Let's go ahead and look at the next slide for what else is included on the SPSS output. So the other two boxes that are important to us on the output for an Anova are what is known as the Anova Table, and then also the bottom one, which is known as the Robust Test of Equality of Means Table. So what these are going to be important for us, and we could go into much greater detail if we had more time, but for the sake of this semester, we're going to kind of give you the highlights of what we need to know to take away from this. These are the forks in the road. So as we will see in a few moments, when we get to having to interpret the Levine's test to figure out, do we have equal variances or homogeneity of variances or not, we have to figure out which way we go at that fork in the road. If we can assume equal variances, we are going to report information from the Anova box. That's really where we want to be working with. If we fail to meet that assumption, we have to have a backup plan. And the backup plan is what is known as a robust test of equality of means. So let's take a quick look at these before we dive into this in more detail. First, the Anova box, you'll notice if you look over to the right-hand side of it, it has our F statistic. That's what we really want to be working with. But if we fail to meet the assumption of equal variances, that F statistic is not a valid representation of what our sample is telling us. So we need to have a backup plan. The backup plan is known as a robust test. There are several of them out there. The one that I typically use as a fallback is called the Welch Test. There's also one called the Brown-Forsyth, so there's a couple out there. But the robust test acts a lot like an F test. It just has the name Welch. And you'll notice, in fact, at that robust test of equality of means box, if you look at the footnote A, it says asymptotically F distributed. That's just telling us that the Welch statistic behaves an awful lot like the F statistic. So we can interpret it just like we would the normal Anova F statistic. And we'll see that as we go through some of our examples when we have to make that choice. All right, so let's go ahead and dive into our hypothesis testing steps. So let's go on to the next slide. So in this particular question, we start off with our statement of research question. So we ask the question, is there a significant difference in starting salaries for law enforcement officers between different communities? So I look at our descriptive statistics box that we saw a couple slides ago, where once again, we have the dependent variable annual salary listed down below it. Then in our very first column, we have the different levels of our factor being the location. And then we noticed, as we said before, that it appears that people in urban environments have higher starting salaries than the other environments. But is that enough to say that we can therefore conclude that that would happen in the larger population? That's going to be the purpose of going through this actual hypothesis testing. All right, so let's move on to the next question, figure out how do we translate this research question into our competing statistical hypotheses. So next slide. So once again, on this one, we still have HO, our null hypothesis, and we have H1, our research hypothesis. For this one, the null still is no difference. So if you read the blue before we go back to the actual symbols, the blue says there is no difference in the starting salaries between the different community types, just like we've seen in other statistical hypotheses. Then for our research hypothesis, H1, our conclusion would be that there is a difference, and the key word that, and the reason why I underline it, there's a difference somewhere between the different community types. So I'm going to stress that point of looking for it somewhere. So you'll notice, now let's go back to the null hypothesis. So HO, we set it up, if there is no difference in starting salaries, then the mu for the rural environments should equal the mu for the suburban, should equal the mu for the urban. So as we go from rural to suburban to urban, all of the population means would be equal. When we look at the research hypothesis, you'll notice that I write out not all means are equal. Well, why do I do that? Well, because we are now comparing three groups, this test is only going to be able to tell us if there's a difference somewhere across those groups. So rather than me writing like, mu of R is not equal to mu of S is not equal to mu of U, that's only one possibility, that they're all not equal to each other. We can reject the null hypothesis and can conclude that there is a significant difference in starting salaries if we find even one significant difference across the three groups. So it's possible that rural and suburban are not equal, but suburban and urban are roughly equal. Or that rural and suburban are roughly equal, but that suburban and urban are not equal. Or it could be that all three of them are not equal. So you can imagine there's quite a few different, what we're going to call later, there's quite a few pairwise comparisons that can be made across these three groups. And then you can imagine as you add more levels to your independent variable, if you have 4 or 5, the number of sort of what we call pairwise contrast or pairwise comparisons starts to grow really quickly. So when we set up our statistical hypotheses for our Anova test, our research hypothesis, we're just going to write out not all means are equal because we don't know exactly where the difference lies. We're just trying to compare it versus either there is no difference or there's a difference somewhere across the groups. All right, let's go ahead and move on to the next slide. So we're back to our good friend alpha. Another nice quick slide. Alpha, we set it at 0.05. Nothing else to say about that. Let's move right on to step 4. 4, critical value of the test statistic. Now that we're working with Spss Output, we do not need to have critical value charts, so we can move right past this step 2. So let's go ahead and move on to step 5. Now we need to figure out in step 5 the observed value of the test statistic. So just like we did with the independent samples t-test, we need to first check that assumption of equal variances, or the assumption of homogeneity of variances, using our good friend, the Levine's test. So what I have here is I show a snapshot of what that looks like on the output, and what you'll see down there where it says test of homogeneity of variances, and then we have a Levine statistic value, a degrees of freedom 1, a degrees of freedom 2, and then a p-value or a sig. And remember that sig is going to be the important thing for us to look at. So let's move on to the next slide and figure out how do we interpret that p-value or that sig for the Levine's test. So next slide. Levine's test. And just to reiterate what it does, it checks the assumption of homogeneity of variances. It provides us with 2 pieces of information. First, it gives us the Levine statistic, which is actually an F. Okay, if you think about it, the word homogeneity of variances, this is like a mini hypothesis test within a larger hypothesis test. And in fact, the Levine test is an F statistic. So we see a Levine statistic of 1.874. However, most of us are not going to be able to look at that Levine statistic, or that F that's right there, and know whether or not we can assume equal variances. what we need to look at for the Levine's test is the p-value for that Levine statistic. So in blue, you'll notice that's what I have pointed out, the p of 0.188. And let's go on to the next slide to remind ourselves of how we interpret that and how that tells us what we can do with the findings from the Levine's test. So let's move on to the next slide. So to reiterate what we've learned about the Levine's test before, if the p-value for the Levine's test is greater than 0.05, we can assume equal variances, and then we would go and report our overall observed statistic findings from the Anova table. But if the p-value is less than 0.05, then that means we cannot assume equal variances, and we need to have a backup plan. And that's where those robust tests of equality of means come into play. And the one that I mentioned before that we will focus on if we have to use it is known as the Welch Test. Why? Because it behaves and acts a lot like an F. So we can interpret it very much the same way that we would interpret the Anova F. So once again, if the p-value is greater than 0.05, we can assume equal variances and we'll report our overall findings from the Anova table. If we fail to meet that assumption with a p-value less than 0.05, we will turn to reporting the results from the Welch test in that bottom table. For us, now let's look at what's circled in red and written in red on this slide. Our p-value for the Levine's test was 0.1888 or 0.188. So therefore, because it's greater than 0.05, we can assume equal variances. So for the rest of this hypothesis test, I'm only going to focus on information from that circled Anova box. So let's go ahead and figure out what we need to take away from that box. Let's move on to the next slide. So just like we did with the independent samples t-test, we want to find not just the observed value of the test statistic that we're reporting, we also need to report the associated degrees of freedom. And you may recall from our previous lecture that for the Anova test, or for the F distribution, we now have two important degrees of freedom. We have both the degrees of freedom between and a degrees of freedom within. So let's figure out where we can find all this stuff on the Anova table. So the first thing we have to figure out is the value of our observed test statistic. Since we were able to meet the assumption of equal variances, we can go ahead and report the actual F statistic from the Anova table. So that's what you see in red, that 12.762, and I have an arrow pointing to it. Then I need to figure out what are the associated degrees of freedom that I also need to report alongside that F. There are two of them, degrees of freedom between, degrees of freedom within. In the Anova table, you'll notice that there's a column that's labeled DF, degrees of freedom. So even though there's three values there, a 2, a 15, a 17, only two of those are important to us. The 2, and if you look at the row it's in, that is our degrees of freedom between groups. So we want to make sure we report that. And then also that 15, the degrees of freedom within groups. Those are the two that we would report. The degrees of freedom total, that 17, we don't care about that as far as reporting out our findings. And in fact, all it is 2 plus 15 equals 17. So there's not a whole lot that we need to worry about with that. So we want to be able to find our observed test statistic, the F, and we also want to be able to find the degrees of freedom between and the degrees of freedom within. So we've got those ready to report at the end of our hypothesis test. Let's move on to the next slide. So how do we figure out step 6? How do we figure out our test decision to either reject or fail to reject the null hypothesis? Similar to what we've seen with the t-test that we did previously, we need to find the p-value for the observed test statistic. And so remember, once again, this is the sig for our actual Anova F. This does not have anything to do with the Levine's test or any of that stuff. We already went over that. Now we are at the step where we want the p-value that's associated with our F statistic, and it's right next to it in the Anova table, and it's just labeled sig. You'll also notice that the sig, it doesn't say sig two-tailed like it did with the t-test. Why? Because as we saw with the previous lecture, the F distribution, because it's based on variance, is really only a one-tailed test, even if you're testing a non-directional question. So it just says sig. So it's right next to the F. We see that the sig is 0.001, so we're going to use that to make our final decision for this hypothesis test. So let's move on to the next slide to figure out, make sure we're interpreting that p-value of 0.001 correctly. Next slide. So when we look at the p-value of 0.001, the way that we know whether or not we can reject or fail to reject the null hypothesis is to go by the language of if p is less than 0.05, we reject the null hypothesis and conclude that H1 is true. If the p is greater than 0.05, we fail to reject the null hypothesis. So for us, we look at that sig or that p-value, it's 0.001. Clearly, that is less than 0.05, so we're going to reject the null hypothesis for this particular ANOVA. Let's move on to the next slide to talk about how we interpret that. We were able to reject the null hypothesis. And similar to what we've seen with other tests, we have a pretty nice, concise way to present our findings. So as you'll see here, we make sure we identify the statistic we were using in blue, F. Then in the parentheses next to the F, we have the degrees of freedom. We have two important ones now. The 2 is the degrees of freedom between. The 15 is the degrees of freedom within. Then in green, we have the observed value of our F statistic, which was positive 12.762. And finally, in that orangish brown, whatever that color is, we report the p-value for the observed F statistic of 0.001. And we can write up a nice little summary, as we see down at the very bottom of this slide, based upon the results of a single factor between subjects ANOVA, or you could have just said one-way ANOVA. We can conclude that there is a significant difference in starting salaries between different communities, and we incorporate that information down there at the end of our sentence. Okay, so here's the important thing about ANOVA. We went through the setup, we got our null and alternative hypotheses set up, we determined alpha, we went through the Levine's test to figure out whether or not we could assume equal variances or not. We found our observed test statistic and the degrees of freedom and the p-value and all that sort of good stuff. And here we are at step 6, and we say, okay, there is a significant difference in starting salary somewhere. And that's the word that I talked about earlier, but somewhere across the 3 different communities. We don't know from what we look at on this slide where the significant difference or differences lie. We don't know if all 3 communities are significantly different. We don't know if it's just rural is different from urban or just different from suburban or some other, what we called before, pairwise comparison. We don't know where the difference lies. How do we figure out where the difference or differences lie, the pairwise differences? This is one thing that we add on now that we did not see before with the t-test. With the ANOVA, we can add on what is known as a post-hoc test. And these are called post-hoc tests for pairwise comparisons. And SPSS is really good at it, and all you have to do is select it when you're running the ANOVA, and then it will just, there's actually several that we'll see on the next slide, and you just pick the right one. And for the sake of this semester, we're not going to go into too much detail, but I want to at least introduce you to the concept of these pairwise comparison tests or these post-hoc tests so that you're familiar and you can use them going forward. So let's move on to the next slide so I can talk a little bit more about that. So next slide. On this slide, we see a snapshot or a screenshot of the SPSS option for selecting a post-hoc test for pairwise comparisons. And as you can see with what I have circled here in red, there are quite a few different post-hoc tests that we can use. And you'll notice on this slide, we see that what is circled in red, it says at the top of it says equal variances assumed. So all of those tests that are listed there, the LSD, the Bonferroni, the SIDAC, the Sheffey, the RGF, the Tukey's B, the Waller-Duncan, all these ones. These are all what we call post hoc tests for pairwise comparisons that you can select. And what these would tell us is simply by selecting them, they would give us output, and it pretty much runs a bunch of small t-tests. It looks at what are all the potential pairs of combinations that I could be comparing. Rural versus urban suburban versus suburban, etc. Right? So it goes through all the pairwise comparisons that could be done, and it tells you which ones are statistically significant. Depending upon the nature of your data, you may want to pick one or more of these types of tests. For the sake of this semester, we're not going to go into it. There's two on here that are sort of like the fallback go-to. So if you ever find yourself going like, oh, I don't know what to pick, I just need to pick something. The number one that I typically go with is the Bonferroni. The Bonferroni is sort of a catch-all. Depending upon the nature of your data, it works really well. The second is the Tukey's B. Those are the two that I kind of go with, and if I don't know much about the nature of the variance or covariance or all sorts of other fancy terms that my data have. So Bonferroni is a good one. Tukey's B is also a good one. But you'll notice, if you ever run a post hoc test for pairwise comparisons, we have to make sure we are picking the correct one depending upon the results of our Levine's test. Our Levine's test, way back when we, in step 5, we found that we could assume equal variances. And that's why, as we see circled in red on this slide, I would make sure to pick one of these from the equal variances assumed set of tests. If I had failed to meet the assumption of equal variances, and I had gone, and then I want to make sure that I'm picking one from the bottom list, down there where it says equal variances not assumed. And in that case, the go-to one with the equal variances not assumed is usually the Games Howl. That's the one that I've used in the past. So once again, as I said, this is not something for you to be too worried about, at least for the sake of this semester, but I want to at least introduce you to the concept of it so you know it going forward. All right, so that's the conclusion of our first hypothesis test. The next several slides are pretty much going to repeat another hypothesis test, but this time we're going to see how would we approach an ANOVA if we failed to meet that assumption of equal variances. So I'm going to go pretty quick. I'll say a couple things on a few of the slides, but if you're watching this, however medium that you're watching this through, you can always pause if you want to use it as a practice thing, the recording, or excuse me, not the recording, but you can pause the video so that you can walk through it at a slower pace. But I'm going to go through it, give a little bit of time, and then point out a couple facts. So let's go ahead and move into that second hypothesis test. In this hypothesis test, now what we have here is, and this is real data. This is real data from research study I did with several colleagues about 10 years ago, where we were looking at individuals who were coming out of prison, and we wanted to know whether or not there was a differences in substance abuse problems for across different racial and ethnic groups. And so once again, we'll see how it fits nicely for the one-way ANOVA because we have a categorical independent variable or a categorical factor, which is race, ethnicity. And in this case, it happens to have 4 levels or 4 groups to it. So it has a Hispanic Latino group, it has a white non-Hispanic group, it has a black non-Hispanic group, and it has an other non-Hispanic group. And we can see in our descriptives box how that is captured there. Then for our dependent variable, our outcome, was a problem severity scale, substance use problem severity scale, which was a 100 points continuous scale with higher values indicating more problems. So looking at this, and one thing reason why we even did this is we had noticed that there appeared to be disparities across racial or ethnic groups. And in fact, if you look at it, it appears that the white individuals seem to have the highest levels of substance abuse problems, whereas the African American, the black non-Hispanic individuals have the lowest. And this was raising some issues about how we were allocating services and identifying people who were being put into a mandatory substance abuse program. So this were sort of where this came from. And so looking at this, I want to know, well, is there a significant difference across these racial ethnic groups? We also see at the bottom of this slide the Levine's, the test of homogeneity of variances for the Levine's test. So let's move on to the next slide. Once again, we have our Anova test and we have our Welch, our robust test box. So remember, which one of these I'm going to use all depends upon my results from the Levine's test. So let's walk through some of the steps and take a look at these things. Next slide. We start off with our statement of research question. You can go through it, take a look at it, and then I'm going to move on to the next slide. Statistical hypotheses. In this case, you'll notice that the research hypothesis, H1, is still written not all means are equal, just like we did on the previous one. But the null hypothesis, the main difference from our previous example is that now that since we have 4 different levels to the racial ethnic group variable, I had to make sure I represented all 4 groups: Hispanic, white, black, and other. Next slide. Level of significance, alpha, it's at 0.05. Next slide. Value, we've talked about this. Let's move on to the next slide. Now this is where this one's going to differ from what we saw on our previous example. Before we can report our observed value of the test statistic, we need to review that test for homogeneity of variances, and we look at the Levine's test. And you'll notice here the sig, or the p-value, is 0.000. So it doesn't mean it's absolutely 0, it just means it's really small. And they're just, eventually when SPSS rounds out, it just comes out at 0. So on this slide, there's two things I want to point out. One is the same idea with the Levine's test. We will look at the p-value for the Levine's test to figure out whether or not we can assume equal variances. Okay, we've talked about that before. The second thing that I want to make sure I point out to you is how we typically write up our results if our SPSS results show us a sig of 0.000. The usual practice is you don't just write p equals 0.000 because it's not absolutely 0. It's probably like 0.00004 something way out there. So it's a very small value. So what we see here, and you'll notice in blue I have written to represent the p-value, I say p is less than 0.001. I don't say it's equal to anything, I say it's less than 0.001 because from the output itself, I don't know exactly what the p-value is, but I know it's really small. So the general practice is when you see that 0.000, you just represent it with a p less than 0.001. Let's move on to the next step. Okay, in this case, what we see with the results of the Levine's test is, it is in fact a p-value that is less than 0.05. So we cannot assume equal variances. So unfortunately, we cannot use that Anova table and the F statistic there. Instead, what we have to report is the Welch results. But because the Welch behaves very much like an F test, we can go ahead and report the results in very similar fashion. Let's move on to the next slide. Now here's what I'm talking about where we say it behaves very much like the F test. Even though we're reporting the Welch, and we'll call it the Welch statistic as opposed to trying to call it the F or something like that, we're going to report the actual Welch statistic, 15.895. And then we still have 2 degrees of freedom. We don't call them degrees of freedom between and degrees of freedom within. It's actually very simple. It's just DF1 and DF2. But they behave just like the degrees of freedom between and degrees of freedom within. So if I have to report something from the Welch or from the robust test table, I still want to report the actual statistic, the Welch, as well as its 2 associated degrees of freedom, DF1 and DF2. Move on to the next slide. Finally, in order to make my test decision of rejecting or failing to reject the null hypothesis, I'm going to look at that sig, or that p-value, for the Welch statistic, since that's the one I chose. And once again, you see here that the sig is 0.000. So you'll see on the next slide how we'll write that out as, rather than saying p equals 0.000, we're going to write p is less than 0.001. So let's go ahead and look at our next slide. So based upon this, as you can see here in blue, I have written down the p-value for the Welch statistic as p is less than 0.001. Because that is less than 0.05, we can reject the null hypothesis and conclude that there is a significant outcome. Let's take a look on our final slide how we would write that up. Or not final slide, I think it's second to last slide. So for here, this is our overall conclusion. We can say we rejected the null hypothesis and we present our findings very similar to how we've done with other tests. The only difference here is since I was unable to assume equal variances and I had to turn to the Welch, you'll notice that in blue, I write the actual name of the statistic I ended up using, which is called the Welch statistic. Then I have the two associated degrees of freedom, the 3 and the 116.894. Then in green, I have the observed value of the Welch statistic. And then finally, I note that the significance is a p less than 0.001. And then I can have a write-up similar to what I see at the bottom of the page based upon the results of a Welch test for equality of means. And that's what I did. Rather than calling it an Anova F test, I put in the name of the test, my backup test, which was that robust test. So results of a Welch test for equality of means, we can conclude that there is a significant difference in substance abuse problem levels between the different racial or ethnic groups. Now, similar to our first example, we rejected the null hypothesis, but we still don't know exactly where the significant differences lie across those 4 different racial ethnic groups. It could be multiple differences across the groups, or it could just be that, you know, the white individuals were significantly higher than the other 3 groups. We don't know. So we would turn to what we referred to before as a post hoc test for pairwise comparisons. So I'm not going to show you the results of it, but I'm going to show you where you would find that if you were requesting it on using SPSS. So let's look at our final slide for this one. Similar to what we did with our first hypothesis test, I've showed you what the snapshot of where on SPSS, how you would click and look for these post hoc tests. Because though, in this one, we failed to meet the assumption of equal variances, we would probably, or we definitely would want to select one of the post hoc tests from that bottom circled area, the equal variances not assumed tests. And the one that I think I mentioned before, but I'll say it one more time, is the Games HAL is sort of the best like catch-all for the equal variances not assumed. So you can see that this is why interpreting a Levine's test in the Anova is so important, because one, after you interpret that Levine's test for the assumption of homogeneity of variances, that tells you whether or not you're going to report the Anova F or whether you're going to report the robust Welch, right? So that right there is important where you go. And if you end up having a significant outcome and you want to do a post hoc test for pairwise comparisons, you've got to make sure you're also going down the right road and selecting the right ones. For us, with this one, we failed to meet the assumption, so we would have to pick one of those equal variances not assumed tests. In our previous example, we did meet the assumption, so we would have picked one of those top tests in the equal variances assumed section. So I'm going to wrap it up there for this one. This one turned out longer than I had hoped it would, but we're getting close to the end of the semester, so bear with me, and I hope all of you are safe and well. Take care.